So now we are going to see about continuity of a function. So let f be a function that that maps E to R, where R is a metric space, where E is a metric space, and it it is a subset of RD. Let me write it again. Yeah, it is a subset of RD. Then f is said to be continuous at a point P if limit of the function at point P is equals to the value of function at point P. What does it mean? It means that, for example, if we have this x, we have this y, and we have this function, then it is continuous if when we at this point P, if when we approach from this direction and from this direction, then the value that the function is approaching is equal to the value at this particular point P. That is, the value near the at the neighborhood of the function is almost equal to the value of the function at the point P. Equivalently, we can also write it as, for every epsilon greater than 0, there exists some delta greater than 0 such that the distance of the point of x from point P, whenever the distance of any point x from the point P is less than epsilon, then it implies that distance of the function from the value of function at P the value of function at the point P is less than delta. So how can we visualize it? So whenever we have a function here, and whenever this is P, then if we have x here, then whenever this distance is less than epsilon prime, then this distance is, if this distance say alpha, if alpha is less than epsilon, then the value of this function, say this value of function, this is fp, this is fx. So this distance is say beta is less than delta. So this is the definition of continuity. Now we will see uniform continuity. It is basically extension of the continuity concept. Whenever we have for any like there we had a P, here P can be any point. For every point, at every point, if it follows the previous condition, this one, P can be any point, not just one point. For all point P, it follows like this, then it is called uniform continuous. So let's state it. Let f be the function again, E be a subset of say some RD mapping to Y. Then F is said to be uniform continuous if for any epsilon, for all epsilon, there exists delta such that F, whenever distance of one point Fx from any other point Fy is less than epsilon, this implies that the distance of x from y is less than delta. Or in other way we can say that if distance of x comma y is less than delta, this implies that distance of f of x and f of y is less than epsilon. So the difference here, we see that in previous case it was for any point, one point P, it need to be continuous at, if it is called to be continuous at this point P if it follows this condition, and if this P can be any point in a function, given function, if for every point, say if it follows this condition here also, if we call this point as P and it follows here also, that is at any point it follows the condition, then it is called to be uniform continuous. Now we see a differentiation. So differentiation, so any function f that maps from A to B, let this be any closed set, to R, then and for any x that belongs to this A to B. So once again, so this f is a function that maps from from a closed set A to B to R. Then and for any x belonging to A to B, it is the function is said to be differentiable at point x if ft minus fx divided by t minus x t tends to 0 equals a finite number. Finite, you can say whatever alpha, something less than infinity, and greater than minus infinity. So then it is called differentiable at this point x. So what is t here? T is any point that belongs to A to B other than x itself, otherwise it will blow off. This will go off to infinity. So now, after having talked about differentiation, let's again go to Lipschitz continuity. So for a uniformly continuous function f is said to be Lipschitz continuous if there exists k greater than or equal to 0, such that whenever this ratio of distance of fx comma fy divided by this ratio of x comma y is less than equals to k, that is in this function the slope is less than some constant, then it is some constant k, then it is called Lipschitz continuous. For example, you can understand it this way. For example, this function goes here, so this slope actually equals infinity, so you can't bound it by any constant k. So this is not Lipschitz continuous. So you can see here, for example, this one this goes like this. so it is continuous, but its slope increases to infinity, so almost infinity. So this is not Lipschitz continuous. So what did we study today? This continuous function f, continuous when limit of f of x whenever x tends to p is equals to q, which is equals to f of p, then it is called continuous. And this is called uniformly continuous. Okay, we also studied alternate form of this, that was for whenever distance of x from p, x being any point belonging to the domain of f, is less than epsilon, then there exists some delta such that distance of fx from q is less than delta, where q is equals to limit is called the limit of this limit of fx, x tends to p, and in this case we can say q is equals to f of p. So this is called continuous, and for uniform continuous this condition actually is valid for all points. That is, at any function, for you take any point, p is not any unique point, p is any point, this holds true. That is, distance of x comma y is less than, say, epsilon. This implies that distance of f of x from f of y is less than delta. So this is called uniform continuous. Then we saw differentiation. Before that, let's talk about this Lipschitz itself. So for there exists some k greater than 0, such that k greater than equal to 0, such that the slope of slope fx comma fy divided by distance of x comma y is less than k. That is, the slope never blows up to infinity. Then we saw differentiability, where we saw that for any function f, it is called its derivative f tax is said to be said to exist and it equals this limit ft minus fx divided by limit tends to x, minus x. Whenever this limit exists, then we say that f is differentiable and its derivative f prime x equals this limit. So this is enough for today. We will meet again in the next video.